Okay, so we've done two examples now of solutions of first-order linear differential equations. And the first one we did was dy by dx plus 2y is equal to x. And the solution we found for this was that y was equal to x over 2 minus a quarter plus a constant times e to the power of minus 2x. And the second one we did was dy by dx, just remind myself what it was. Oh yes. The second one we did was dy by dx plus y over x is equal to the sine of 2 of x. And the solution we got for this one, let's put some implication signs here. I hope that doesn't pick up on camera. My stomach's rumbling. The solution we got for that one was that y was equal to minus a half cosine 2x plus 1 over 4x sine of 2x plus c over x. Okay, so if we look at both of these, you can see that they're both of a quite a similar form. Both of these solutions we can write in the form y is equal to what's called a particular integral plus what we call the complementary function. So what do I mean by those things? Well, by the particular integral, let's call this ypi. That's a particular solution to this differential equation. So, for example, here, the particular integral is x over 2 minus a quarter. And here, the particular integral is minus half cos 2x plus 1 over 2x sine of 2x. So this is going to be a solution of this differential equation. So the particular integral is any solution of the original differential equation, which in general is dy by dx plus p of x y is equal to q of x. Any solution we can find at all. And the complementary function, ycf, is actually a solution of dy by dx plus p of x y is equal to 0. So it's the solution of the equation where the right-hand side here is 0. So, and you can figure this out for yourself by just playing with these. So, for example, let's do a particular example here. In this equation here, in the second equation, ypi, the particular integral, was equal to minus a half cos 2x plus 1 over 4x sine of 2x. And I'll leave it as an exercise for you to do. But what you can do is you can differentiate this with respect to x and check to see whether dy pi by dx plus ypi over x is equal to sine of 2x. So the particular integral here that we found from this differential equation is minus a half cos 2x plus 1 over 4x sine 2x. And if you substitute that into the left-hand side of the differential equation, you have to differentiate it to get dy pi by dx, and then you substitute that in there. Then you get sine of 2x appearing on the right-hand side. And the complementary function is this bit with the integrating constant in. And so that's a solution of dy by dx plus p of x y is equal to 0. So in this particular case, our complementary function, in this example, is ycf is equal to c over x. And again, if you differentiate this, you can satisfy yourself that dycf by dx plus ycf over x is equal to 0. You just have to differentiate it and put it in there. Okay, so what happens when you multiply, what happens when you add the particular integral and the complementary function together and put them all into this function y? Well, when you put this function y now into the left-hand side of the differential equation, then the particular integral part of y gives you the sine 2x on the right-hand side, whereas the complementary function part of the integral of the solution gives you 0 on the right-hand side. So when you've added these two things together, put them both in there, you get sine of 2x plus 0, which is, of course, equal to sine of 2x. So that means if you can add your particular integral and complementary function together, then this is always going to be a solution of the differential equation you first thought of. So what does this give us? This gives us an alternative way of trying to solve a differential equation, which is the method you'll actually learn if you start solving second-order differential equations with constant coefficients. That's a reference, I guess, to another podcast. So very quickly, how might you use this information? Well, if all our solutions are of the form of a particular integral plus a complementary function, what it means is if we can guess or figure out by some means any solution to our differential equation, and we can work out a solution of for the complementary function, which is the differential equation with 0 on the right-hand side, then we're away. We've found a solution to this differential equation. So just to give a quick example of that, let's try and solve this top differential equation here by this means. Okay, so the first thing we're after is a complementary function, which you need to find a solution to dy by dx plus 2y is equal to 0. Remember, we're after the solution when q is equal to 0. And we're going to guess a solution of the form y is equal to e to the power of lambda x. Now we differentiate that. That gives us dy by dx is equal to lambda e to the lambda x. We put those two in here. We get lambda e to the power of lambda x plus 2 e to the power of lambda x is equal to 0. And we can cancel through. We can get rid of our e to the lambda x's, because neither of those are going to equal 0. And so we end up with lambda plus 2 is equal to 0. So lambda is equal to minus 2. So we can see straight away that our complementary function ycf is equal to something of the form e to the lambda x. Now, if I put an arbitrary constant in here, that's going to give me exactly the same equation at the end. So that's going to give me some constant times e to the power of minus 2 of x, and that's still going to work. Then the last thing we have to do is we have to guess, by some means or other, any solution to this equation. Okay, so if we get a solution to this equation, let's guess a particular integral. Now we've got a linear function of x here on the right-hand side. So if we guess y pi is equal to ax plus b, then dy pi by dx must just equal a. We differentiate ax plus b, we get a. And then we substitute that in here, and that tells us that a, that's dy by dx, plus 2 lots of ax plus b has got to equal x. Well, all the terms proportional to x must be the same on both sides of this equation. And here we see we've got 2 times a times x is equal to x. That tells us that 2a has got to equal 1, or a has got to equal a half. And we have a plus 2b is equal to 0. And so if a is equal to a half, then the only value of b that would work there is that b is equal to minus a quarter. And you can satisfy yourself that those two values of a and b satisfy these two equations. So that tells us that our particular integral is equal to 1/2 times x plus b, and b is equal to -1/4. So by guesswork, we've managed to solve this differential equation because we found a complementary function and we found a particular integral, and we know that our solution is equal to the particular integral plus the complementary function, which is exactly the solution we found earlier. Y is equal to our particular integral plus our complementary function. So that provides a second method for trying to solve first-order linear differential equations. To be honest, the time it's most useful is when p of x is just a constant, because it allows you to guess solutions of this form for your complementary function. Okay, so I've covered now two different ways of solving first-order linear differential equations. The first one is the most general method. It's using an integrating factor. The second method recognizes that all the solutions you get of linear first-order differential equations are of the form a particular integral plus a complementary function. And if you're able to guess particular solutions to your differential equations, then this provides an alternative way of solving them.